everyone, and welcome to PyData Global. This is the final session in the machine learning and AI track for the second day of PyData Global. Just a bit of housekeeping for those who are just joining the PyData Global event. You feel free to use the chat to connect with fellow attendees and share your thoughts. If you have any questions, please post them in the Q&A tab, and we will address them at the end of the session. So with that, it's now my absolute pleasure to introduce Mohit and Dylan, who will be giving a talk titled UQLM, Detecting LLM Hallucinations with Uncertainty Qualification in Python. Great. So with that, I hope you'll give them a warm virtual welcome. And with that, I'll hand the stage over to, I think Dylan's going to get us started.
Great. Thank you for the introduction. So I'm here with my colleague Mohit today. We're going to talk about our open source Python library called UQLM for hallucination detection using uncertainty quantification. So the plan for the talk today, I'm going to give a quick overview of what are hallucinations and what was the motivation for why we built UQLM. I'll go through how these methods work under the hood and how to implement them with the UQLM software. And then I'll hand it over to Mohit, who will go through some of our experiments from our research and share some results on real data. So just to start with some motivation for the project. So we've got some, I think, notorious examples of hallucinations here that I think are a little bit entertaining. But we have one example where Gemini is telling a Google user that they should put glue on their pizza to keep the cheese from falling off. Another example where Gemini is telling the user that they should eat at least one rock per day per the recommendation of UC Berkeley geologists. And then another example, which I think is maybe the most famous example, is ChatGPT miscounting the number of R's in the word strawberry. And in this example, is willing to bet $1 million that there are 2 R's in strawberries. So these are really blatant examples of hallucinations, but it's not always so obvious. So I think a persistent challenge around hallucinations is that often the content sounds plausible when it's generated by an LLM, but there are in fact mistakes in it or hallucinations. So for the purpose of this talk, whenever we're talking about hallucinations, we're always talking about content that's non-factual and a generated response from an LLM. So you see different definitions of hallucinations depending on the context and depending on who you ask. But for our purposes here, we're talking about non-factual content and generations. So if you talk to folks who work with LLMs, who build, LLM-powered systems, applications, you'll hear a lot about, well, we don't have to worry about hallucinations because we have human in the loop. But human in the loop has very important limitations. So in my experience, I think human in the loop is something that's often not well defined as far as its scope. So I've seen it mean anything from doing, like, on one end of the spectrum, exhaustive human review, where humans are fact-checking every single LLM output. In that type of human in the loop, where you have like exhaustive fact-checking, a lot of the time we're dealing with prohibitively large use cases dealing with hundreds of tens of thousands or even 100,000, for example, generations, and we can't have, it's just too large of a scale to do exhaustive human fact-checking. And for a lot of use cases, if you're doing exhaustive human fact-checking, it kind of defeats the purpose of using the LLM. On the other end of the spectrum, it could be anything, as little as kind of vibe checking, a small sample of responses. So this sort of like arbitrary sampling based human in the loop, where you're sampling a set of responses because you can't review them all and you're reviewing that subset, is of course not going to be sufficient for hallucination management. So then it brings us to, like, what about computational methods for hallucination detection? So we have ground truth based hallucination detection, which is you have a set of questions, you have the LLM generate responses to those questions, you compare the generated responses to an answer key, and you kind of use that like answer key based grading as a way to evaluate the performance of that LLM. Now, this is very useful for kind of offline evaluation, maybe like pre-deployment assessments or kind of retrospective assessments, but we don't have the answer key at generation time in deployment. So this collection of methods doesn't help us at generation time. We're interested in for our problem here, we're interested in detecting hallucinations at generation time. And then you have like the RAG specific or retrieval augmented generation specific approaches, where you have the retrieved or the source content, the generated content, and you're kind of looking at the faithfulness between, or the overlap in a sense, between the generated content and the source content. Those methods are very useful for RAG. But what about non-RAG use cases when you don't have this source content, this reference text to compare to?
Dylan,
and then also like those.
Dylan, I'm sorry,
Yes.
but I think we've lost your slides.
Oh, let me try sharing again. Are they back?
Yes, they're back, and this is the one with we've got the shrug.
Okay.
So I think.
Great. So I was saying the RAG specific approaches, they're specific to RAG, and we don't have that reference text, then those approaches don't help us, and also that they don't look at the kind of inherent uncertainty in the generation process. So we were interested in focusing on uncertainty quantification for a couple of reasons. One is we wanted to detect hallucinations in a closed book fashion, meaning we're doing so without any reference text, no ground truth text, no retrieved text, and doing so at generation time. So not kind of retrospectively, but like at the time of generation. And this is where uncertainty quantification shines. So when Mohit and I were doing our literature review on different hallucination detection methods, what we noticed is for uncertainty quantification methods, there's a huge gap. We saw there was a huge gap between the research and the open source community. So the research had a lot of amazing methods that have been shown to be very effective for hallucination detection, but the adoption was largely limited to researchers, and there wasn't a lot of open source tooling that kind of made these techniques accessible for non-specialized practitioners. And so that's what we set out to do with UQLM, is make it so developers could come with zero prior knowledge of these methods, and just use them out of the box for hallucination detection. All right, so we built UQLM, which is an acronym for uncertainty quantification for language models. UQLM is a Python package that provides response level confidence scores at generation time to be used for hallucination detection. And these confidence scores are based on uncertainty quantification methods. So at a high level, I'll go through these different methods in more detail. But the different families of scoring methods for UQLM are as follows. So we have consistency-based confidence. The idea here is to take advantage of the fact that LLMs are not deterministic. We generate multiple responses to the same prompt, and we measure kind of the semantic consistency of those responses as a way to measure confidence. Token probability-based confidence. This just takes the token probabilities from the response's metadata and then does some statistical calculations on those. LLM as a judge is just using another LLM to evaluate the correctness of a response. And then our contribution from our research, Mohit and myself, we came up with an ensemble approach that can fuse any of these aforementioned techniques, any combination of them, and be trained to optimize for like an optimized combination that's optimized for a specific use case. So we'll talk more about what these really mean under the hood, but at a high level, that's how they work. So all these different methods give response level confidence score ranging from 0 to 1. 1 means higher confidence, lower hallucination likelihood. And as just to keep in mind as we're going through the different approaches in the software, et cetera, for the rest of the talk, how these scores or scoring methods can be used in practice. So one way that they can be used, maybe the strictest way to use these response level confidence scores, is to simply disallow responses that have confidence below a certain threshold. So if the confidence score is less than some threshold that you specify, we're just going to disallow the response. That's maybe useful for like very sensitive use cases where you really want to prevent incorrect responses. Back to the human in the loop conversation. In scenarios where exhaustive human fact-checking is infeasible, which I think is most of the time, and you want something better than arbitrary sampling-based review, maybe you have like 10,000 generated responses and a human only has time to review 200. Which 200 do you review? Well, you probably want to review the 200 that are most likely to contain mistakes. So you can prioritize, you can use these confidence scores to kind of sort them based on highest uncertainty to lowest uncertainty, or highest confidence to lowest confidence, and use that to kind of get the highest returns on those human review hours. So you review those that are most likely to contain mistakes. Or maybe you want to allow the response to the end user, but you just give them a disclaimer. It says, hey, this response may contain a hallucination. Double check that it's correct, or something like that.
Dylan, we lost your slides again.
Okay, let me try. Let me get back to sharing again. Sorry about that. Are we back?
Yes.
Okay. So let's talk about how these methods work under the hood and how they're implemented with the UQLM software. So first family of scoring methods is consistency-based confidence. In literature, this is called black box uncertainty quantification. The idea here is we're taking advantage of the non-deterministic nature of LLMs, generating multiple responses to the same prompt, and then measuring semantic consistency. So we have like a workflow example here. We ask the LLM, what is the capital of France? We generate an original response. This is the response we're going to score. We're going to attribute a confidence score to this response. This is the one under audit. We increase the temperature parameter, which controls the degree of randomness. And we generate a set of sampled responses to that same prompt. And then we pair them up, original versus candidate 1, original versus candidate 2. Remember, these are all generated from the same LLM, from the same prompt. And then we're just measuring the semantic agreement, consistency, similarity of the paired up responses. So we can do these pairwise comparisons using a number of different methods. We can do embeddings-based similarity. We can do natural language inference, entailment, contradiction classification. But then we basically aggregate these pairwise scores to get our confidence score for our original response. So obvious disadvantage of this collection of methods is that you have to pay for these extra generations, so it does add some costs, and these comparisons take time, so it can add some latency. But the nice thing is that they operate only on the outputs of the LLM, and so they're compatible with any LLM. You can use whatever LLM you want with this collection of methods. As far as like the workflow for the user, users of UQLM provide their prompts in their LLM, and then UQLM handles all of this stuff, the generation and scoring under the hood. So the user just has to come with their prompts in their LLM, and then UQLM does the rest. So let's look at how this gets implemented with the software. So just a couple lines of code to put this in practice. So we start with our LLM. We instantiate our LLM object. We can use, here we're using a GPT model, but you can use any of the LLMs that are supported by LangChain. So as long as it's a LangChain chat model class, you can use it. So that's like supports all the major providers. We take our black box UQ class from UQLM. We instantiate the black box UQ class by passing our LLM object, specifying which scoring methods we want to use, which scores we want to use among the black box scorers. Here I've just specified 1, but we can specify 2 or 5 or however many we want. And then once we've instantiated our black box UQ object, we can implement the generate and score method. So this is a method that's available for all the different classes that correspond to those different scoring methods: black box, consistency-based, token probability-based, judge-based scoring, or ensemble-based scoring. They all have this generate and score method, and we'll go through those examples too. But it does exactly what it sounds like. It generates responses to the provided prompts, and it scores them using the specified scorers. So we have our prompt. What gets returned is you have your prompt, you have your response, you can see the metadata, like the sampled responses that were used to compute the confidence score, and then you have the associated confidence score of the response. So just to give a sense of like the intuition for what this is doing, we have like in the first 3 examples here, the response being scored has perfect semantic consistency with the responses the sampled responses they're being compared to. So we have the maximum possible confidence for those 3 responses. But if we look at the next 2 examples, where the responses are 8 and 20, we see there's a lot of contradictions between the response being scored and then those sampled responses. And what that means is we have lower confidence for those responses. Those are much more likely to contain a hallucination. If you ask the same question 6 times and you get 6 different answers, how much can you trust the answer, right? So that's the idea. We also have this nice feature with BlackBox-UQ where you can specify use best as true. And what that does is it actually looks at not just the original response, but all the sampled responses. And then it may swap it out to make sure that your original response, the response that's being used, is the one that's least likely to contain a hallucination. So that's kind of a nice feature. Okay, moving on to the second collection of methods. So token probability-based confidence or white box uncertainty quantification. These methods use the token probabilities in the generated response to compute uncertainty or confidence. So we've got a super simple example here, just illustrative example. Who was the first president of the United States? Gets fed to the LLM. The LLM says it was George Bush. And then like a really simple example of how those tokens map to token probabilities. So everything looks good up until the 3rd token. And then for the 4th, the 4th token should of course be Washington. So there's a low probability associated with that token. In this example, this is just the confidence score is just the geometric mean of these token probabilities. But there are a lot more sophisticated white box methods. You can see there's quite a few here. Many of these white box methods require only that single generation. And so what that means is those methods, the single generation white box methods, don't add any cost because there's no additional generations, and there's negligible impact on latency because we're not doing these like semantic comparisons and we don't have those additional generation steps. The disadvantage of the white box methods is that not all APIs expose these token probabilities, and so these methods are not compatible with all LLMs. There are a lot of LLMs that won't work with these. And like I said, we have this is a really simple example, but we have a lot more sophisticated examples too. Sophisticated scoring methods too. Okay, so putting it into practice, how does it look with UQLM? So very similar, just a few lines of code. We take our white box UQ class. We can instantiate it by passing an LLM object. Again, here I'm using a Gemini model, but you can use whatever model you want. Specify which scores we want to use. Again, I'm using just a single score for this illustrative example, but you can use like any number of the white box scorers. And then we run the generate and score method. So that's kind of the common theme among these different classes is they all have this generate and score method that does exactly that, generates your responses, and then scores them with whatever scores you specify. Same workflow from the user's perspective as with BlackBox-UQ. Instantiate with your LLM, generate and score with your list of prompts. Third, we have LLM as a judge. So the idea here is to take a prompt, give it to our original LLM, take the generated response from our original LLM, and then concatenate the question response pair. So we concatenate these, we form a string concatenation of the question and the generated response, and then we feed that concatenation prepended with some instructions to evaluate its correctness to one or more judge LLMs. Maybe you have one LLM judge, maybe you have 5, whatever your workflow looks like. The judges each form a judgment on the correctness of that response to that question. Again, this is closed book, so there's no like reference answer or anything. It's just looking at the question response concatenation, and then that judgment maps to a numerical score between 0 and 1. So we have different templates available out of the box for how this scoring can look. We can do binary, just correct or incorrect, which map to 1 and 0. We can do 3 categories, correct, incorrect, uncertain, to add like a 0.5 score. We can do continuous, just any value between 0 and 1. We can do Likert scale, which is like very bad, neutral, good, very good type of thing. Workflow, consistent with the previous 2 types of scoring methods. User provides their prompts, their LLM, and of course here they would also provide their judge LLMs, and then UQLM does all of this: generate the original response, concatenate it with a question, feed it to the judges, get the judgments, get the scores, and aggregate them into a confidence score, which is attributed to our original response. Okay. Similar process for how to use the API to implement this workflow. So here we have some different examples, different LLMs. So we need to instantiate both our original LLM and then our judge LLMs. You import the LLM panel class, panel for like panel of judges. We thought that was kind of fun and clever. When you instantiate the LLM panel class, you pass your original LLM, you pass your list of LLM judge objects, and then same thing, generate and score from a list of prompts. Here we get, of course, the generated response. We get the judgments from the individual judges, and then we get different aggregations of those that can be used as confidence scores, depending on what your preference is. Notice like we've been using different LLMs in all the different examples. This is just to create some variation in the examples, but like you can pick whatever LLM you want, so long as it's supported by LangChain. Okay, and then lastly, just wanted to go through, before I hand it over to Mohit, the ensemble method that we came up with. This was the contribution of our research on this topic. But we had this idea of like, what if we fuse the different, some combination of black box scores, white box scores, and judges into an ensemble that's trained on data from a specific use case? Can we improve hallucination detection performance over the individual scores? That's kind of what we set out to find. So the way that the training of the ensemble works, you take your LLM that you're going to use, you take a representative sample of prompts. So this is important, a representative sample of prompts from your use case. So if your use case is math questions, you take a sample of math questions. If it's history questions, you take a sample of history questions. Whatever your use case is, you take a representative sample of prompts, you generate and score with your whatever scores you want to include in the ensemble. So that's what we get here. We get the generated response, and then we get the scores from each of the different scores that we want to include in the ensemble. So when we train the ensemble, this is actually our feature vector, right? So this is like one observation. This is another observation. And the features are just the outputs from the individual scoring methods that we've been talking about. So these are our feature, this is a feature vector. And then to get our labels, we take those generated responses and we grade them against an answer key. So, Paris is the right answer to this question. This is correct. 2 is the wrong answer to this question. So this is incorrect. So what we're getting is we're getting binary labels of whether these responses actually contain hallucinations. These are like predictors of whether there's hallucinations. So our features, our labels, and then we just train a classifier. You can do random forest, you can do logistic regression, you can do whatever classifier is your favorite. But the idea here is like we're just creating the training data set to train the ensemble, whatever classifier, again, you choose. And what the classifier is effectively picking up once it's trained is the relative importance of the different scores for this specific use case. And Mohit's going to show like we actually find this does lead to better performance once you optimize for a specific use case. So with that, I will hand it over to Mohit.
Thank you, Dylan, and good afternoon, everyone. My name is Mohit, and I will take you through the experimental section. Next slide, Dylan. So here on the left-hand side, you can see the 6 public benchmark that we used for our benchmark. 2 benchmark included math question, another 2 included multiple choice question, and another 2 included open-ended question. In this talk, I will show you results from 2 benchmark, which were like open-ended, which contains open-ended question. But if you want to see the full results, you can scan the QR code at the top, which will take you to our paper. So here is how we done the experiment. We actually sampled 1,000 questions from each benchmark, which contained question answer dataset. And then we used the question and generated response using various LLMs and computed the response level confidence score using UQLM. Then we wanted to evaluate the effectiveness of UQLM. And in order to do that, we looked into 2 things. First thing is like how does the LLM accuracy will change if you remove the low confidence responses? And second one is like how well does UQLM classify responses as correct or incorrect? Next slide. So let's look into how the LLM accuracy changes. And here, if you see the x-axis, it has threshold, which is the cutoff confidence score. Basically, below that confidence score, we will remove those responses. And on the y-axis, we have filtered LLM accuracy. And you can see the different benchmarks and the LLM that has been used to generate the responses. Here, I want to point out that on the black, if you see the plots, you will see a black dashed line, which is the baseline LLM accuracy. That means then we lost the share. So that black dashed line actually shows you the baseline LLM accuracy, which is if you don't use UQLM and simply generate the responses using that LLM, you will get that accuracy on that benchmark. And then with different curves shows the best accuracy for different categories that Dylan has mentioned. Here, I want to quickly point out one thing. If you see across, if you observe all the plots, there is one common trend, which is basically there is as you increase the threshold, there is a monotonous increasing trend, and which is a very good indicator of that we can actually improve the LLM accuracy by removing the low confidence responses. Next slide, Dylan. And in order to answer the second question, we basically looked into the AU-ROC score. Here you can again see the ranking of different individual scores and the ensemble score based on the AU-ROC score. Here you do see the ensemble score at the top, but in our all experiment, we noticed that hallucination detection, basically the best hallucination detection is basically more than 0.8 in 19 scenarios out of 24. And one thing I would like to point out that even though ensemble score is like best in most of the cases, but individual scorer are also performing very well in identifying that. Next slide. So with those two things as our main results, I would like to point out like what are the new features that is coming to our toolkit. First is the hallucination detection techniques for long text output. For long text output, what we do is basically divide them into different smaller claims, and see if they are true and false. And we do that by assigning each claim uncertainty score. And this can also help to basically mitigate the responses by removing the low confidence claims and combining the remaining claims. Hopefully, these kind of technique will be coming to UQLM in a month or two. And another thing that we are working on is basically hallucination detection techniques for code generation. Basically, for code generation, obviously we cannot use the available technique because they rely on the semantic consistency, which cannot help us with the code consistency. Hopefully, this kinds of technique will be included in UQLM by early 26 or later on. Next slide, Dylan. And thank you everyone for attending this talk. Here is the QR code for our GitHub repository. Feel free to go through it and reach out to us if you have any questions. And if you like the repository, please give it a star.
Great. Thank you so much. That was an excellent talk. So I don't really see any questions at this point in time, but maybe we can take some, maybe if people want to share their thoughts or put some questions in. Okay, so now I see there's a question. How about, I can put that on stage actually, I think, for you. Is there a paper? Oh, okay. Sorry, there's a couple of questions coming in. Just a sec. Let's try this one first. How about evaluating text SQL?
That will be part of the code generation uncertainty quantification that we'll release in 2026.
Okay, great. And the next one would be, here we go. Oops, I think I had it there. Is there a paper or archive preprint of this work?
Yes, I put it in the chat.
There you go. Perfect. I see that. So anything else people would like to ask of Dylan and Mohit? Okay. Well, thank you very much. That was, as I said, that was very interesting. And I'm sure you will get some questions from folks outside of the session once they process it. But thank you. This is the last session for our machine learning and AI. So that was a nice wrap up. Thank you everybody for coming to PyData Global Day 2. We will be back on the stage early tomorrow morning for Day 3. So thank you all. Enjoy the rest of your days. Thank you, Mohit, and thank you, Dylan.